Welcome to the course of solid-state electronic devices. Today we'll be discussing the module number 6, that is a bipolar junction transistor. So more specifically, we'll start with the brief introduction for the bipolar junction transistor, very commonly known as BJT. We'll proceed with the structure of the BJT, its working, operation in various regions, and IV characteristics. BJT is a three-terminal device, its terminals being the emitter, base, and collector. It consists of three types of semiconductors put together. It is made up of two junctions of oppositely doped semiconductor material. Basically, it is going to have two p-n junction diodes back to back. So, either a p-type semiconductor is sandwiched into n-type semiconductor, or the reverse, that is the n-type semiconductor is sandwiched into p-type semiconductor. The most basic feature of BJT is the property that the current through any two of its terminal can be controlled by applying a variable current to the third terminal. That variable current is controllable. So BJT can be controlled by the third terminal. In BJT, both the majority and minority carriers play a role in the operation of the device. Hence the name, that is the bipolar junction transistor, is being given to such a device. The application of BJT are numerous. Few being that it can be used as an amplifier or a switch. So moving towards the structure, BJT consists of two junctions of oppositely doped semiconductor materials. It can be implemented as N-type region between two P-type regions, commonly known as PNP type device, or a P-type region between two N-type regions, known as NPN type of device. In figure, it shows a PNP type transistor with both of its junctions biased. The adjacent figure, that is a PNP transistor, is a representation of a BJT, which is PNP type. Two junctions can be made forward biased or reverse biased independently. So it actually gives four modes of operation, which would be discussed later. As discussed in the structure for the BJT, it consists of the emitter region, base region, and collector region. Emitter and collector region are N-type material. For the NPN type transistor, and base region is the P-type material. These junctions are biased. The forward biased junction emits holes and is thus called the emitter junction. Reverse biased junction collects the holes given by the emitter junction and is thus called the collector junction. The middle N-type region is called the base region. For the ideal PNP transistor, the following two things should be considered while design. Number one, there must be no recombination of injected holes with electrons in the base region before they reach the collector region. So when the emitter region are emitting electron, these electrons should reach the collector region without any recombination at the base. This thing can be made possible by designing the base region narrower as compared to the emitter region. Therefore, the holes do not get time to recombine with the electrons. The next thing is the emitter current must be entirely made up of holes being injected from the emitter. This thing can be achieved by keeping doping concentration of the emitter much higher than that of the base region. So these two things has to be considered while designing the ideal PNP transistor. But in practice, it is not possible. The flow of holes from emitter give rise to the emitter current. Holes cross over the base and enter into the collector region and contribute to the collector current. Ideally, no recombination must occur in the base, but practically some recombination do occur. Therefore, it causes a drift of electrons in the base region which must be supplied by the external current. This external current gives rise to the base current. However, the base current is very less in magnitude as compared to emitter and collector current. So the operation in various regions. Two junctions of the BJT are independently set as forward bias or reverse bias. Therefore, it gives rise to four combinations, that is four modes of operation. These modes can be when the emitter region is forward bias, collector region is forward bias. The mode of operation is the saturation region. If emitter region is forward bias and collector is reverse bias, it gives rise to the active mode of operation. Whereas the emitter region is reverse and the other one, that is a collector junction, is forward bias, it gives rise to the reverse active region. Whereas if both of them are reverse biased, the device operates in the cutoff region. These different regions are depicted in the figure besides the table, that is the operating regions of the BJT, and they also represent the IV characteristics of the BJT. IV characteristics. These are basically the characteristics when we represent the current versus the voltage for a device. If we consider the output characteristics of the BJT, we are having three regions. Basically, the collector current IC versus the VCE. When IC is equal to 0, it corresponds to the cutoff region of the BJT. The cutoff region means that the potential to be given at the base emitter junction is very less than the threshold voltage of the PN junction. Therefore, no conduction is possible in that junction, and we say that the BJT is operating in the cutoff region. As we increase the voltage above the cutoff voltage, the conduction starts happening in the device, and it depends on which region the device is conducting. In this conduction region, the device can conduct in two modes, that is the active and the saturation. So in active region, the large conduction current is there and it is linearly dependent on the voltage. That is, the conduction current linearly increases with respect to the voltage. So as voltage increases beyond, device enters into the saturation. In this region, the base of the BJT is saturated with number of electrons. Therefore, we call it as a saturation region. In the figure, the shaded region. So in the figure, the shaded region is the active region where it is linearly dependent on the voltage. Whereas as soon as the current starts becoming constant, even after increasing the VCE, the device gets into the saturation region, and the cutoff region is a region where the VBE is below the threshold. If we see the adjacent figure, that is the ICE versus the VBE characteristics, it also gives us the notion for these three modes of operation. When the current is not increasing, even after increasing the VBE, the current is almost zero, that region is a cutoff region. But as soon as the device gets into the active mode, the current starts increasing linearly with respect to VBE. This region is the active region. And when the current starts becoming constant with respect to the voltage, that is a VBE, that region gives the saturation region. So the device basically operates in these three modes of operation, and these are the IV characteristics of the BJT. Thank you.